Okay, in this video we'll discuss how to find a complexity from a given recurrence relation. So let's say we have like a recurrence relation like what we have taken before. We'll just take it. So t of n equal to t of n minus 1 plus some constant c is there. So now our aim is to find out we have discussed some of the asymptotic notations before in previous videos, that is some big O of n or big O of some polynomial, then omega of the polynomials, right? So I'll just write n here, then theta notations, then small o and small omega, or little o and little omega. So these 5 asymptotic notations we have discussed. So now today we'll discuss a method to find out the complexity from given recurrence relation. So now big O of n or omega, we'll just see how it will go. So now what is the aim while solving this recurrence relation is, see, we need a complexity for t of n. Okay, and we have to reduce the left hand side t of n we cannot change anything here, but now we have to reduce the t term from the right hand side. So right hand side we have this t term, so this has to go and it should come up with some polynomial in terms of n. Okay, so just a polynomial we should bring. So what we can do, so we can replace, see, this is a decrease and conquer method like what we have discussed before also, that the initial size of problem is n and we are reducing that problem size to n minus 1 at each iteration. So what exactly happening in this problem, n is getting replaced to n minus 1. So now what if I replace n to n minus 1 in this relation, what will happen? I will be getting t of n minus 1 will be equal to, let's have this as a equation number 1. Okay, I'll just for sake I'll give the numbers. Now t of n minus 1 will become t of n minus 2 plus c. Okay, that is equation number small a I'll make. Then again replace n by n minus 1. So what will happen? T of n minus 2 will be equal to t of n minus 3 plus c. That is equation B. Equation C will be t of n minus 3 will become t of n minus 4 plus c. That is our equation C. And similar way we may get t of n minus some arbitrary number k, n minus k, equal to t of n minus k minus 1 plus c. That is, let's say, equation k or something. I will just give it. Okay, so now what we have to do is like our aim is now take from equation 1, like I'll just take from 1. So now we have t of n equal to t of n minus 1 plus c. And now if you look at equation number A, we have t of n minus 1 already calculated here, that is t of n minus 2 plus c. So can I say from 2, like from A now, from A I can write t of n equal to t of n minus 2, t of n minus 2 plus c that is your t of n minus 1, right? And now we had one more c. So this is the case for first one. Now if I go further, like now from B, because we have the formula for t of n minus 2 as well in B, but what this formula simplifies here, t of n equal to, now t of n minus 2 plus 2c. So now again reduce this, like replace t of n minus 2 to n minus 3. So what I will be getting, t of n equal to t of n minus 3 plus c plus 2c. So I will be getting t of n equal to t of n minus 3 plus 3c. So if I proceed same way, I'll be reaching at some point which is t of n equal to, I'll be just going for t of n minus k case. T of n minus k plus k into c. This is what our equation, I'll just write now capital A. So now we have obtained one equation of this form. Now what is our aim? That when this t term will be removed, right? So now our aim is, like I'll just change the color of the pen. So now our aim is to change this term with t to one simple polynomial. And if you remember in recursion, whenever base case is there, this term will be vanishing, right? So the base case, let's say now we generally assume that t of 1 is our base case, right? The first initial case. Because the problem of size n will be divided at decremented each time and it reaches to the initial value like size 1 to size 1 value, right? That is a single problem. That is why it should be t of 1 is our base problem. So now what should be the t of 1 in this case? This n minus k should be equal to 1. So now if I put n minus k equal to 1, that is our t of 1. So what I will be getting, n minus k equal to 1. So I will be getting k equal to n minus 1. So this is what I have got for k equal to equation. And now let's say there is some t of 1. To solve this t of 1, some constant time is needed, and that will be given usually in the example, that how much time will be needed to solve the base case. Okay, so now we will just move further. So we got the value of k, so I will be getting now t of n equal to, I am just equating n minus k to 1. So what will happen in that case? I will be coming here to t of 1 plus k into c. And what is k? N minus 1 into c. Now t of 1, like we have already c here, so we will just choose some base case other value c1. So what I will be getting now, t of n equal to, the time required to solve t of 1 is c into like c1. So time is c1 plus n into c minus c. So our equation in terms of n will become cn plus c1 minus c. So what we can say, that our t of n is simplified as, c into n plus c1 minus c, and we'll just equate c1 minus c to some another variable ck, so that we have cn plus ck. So now we have t of n equal to cn plus ck. So let's say ck is a constant, right? So this is a constant time. So to solve this part of the problem, you need a constant time, and to solve this problem we need a time of size n. So there are some properties of asymptotic notations, like big O of any polynomial. Let's say a x plus b is there, like okay, big O of an plus b is there, alright. So it will be equated to big O of n. If you have a polynomial of this form, big O of a x square plus a n square plus bn plus c, then we can just simplify this to big O of n square, because the highest power of n we are taking, highest degree of n, and with respect to that it is changing. So now if you look at this equation, cn plus ck, so ck is constant and cn is there, so we can get the complexity of given recurrence relation, that is T of n, is now, I can just write it big O of n, big O of Cn plus Ck, which is equal to big O of n. Okay, so a few more videos we'll have by solving some different types of recurrence relation, and then we'll discuss some of the methods of recurrence relations as well.